team in quantum applications and architecture at Intel Labs. And I'd like today to give you a snapshot of the research that's going on up and down the stack at Intel. We're taking very much a systems perspective to quantum computing. First, to just remind you of how different this quantum computing is as a technology. What is a qubit, right? So if you think in a cartoon sense of a classical bit as being either a 0 or a 1, either instead, it can be the same as like for a coin, which is either instead heads or tails, right? The principle of superposition, a qubit, is like a spinning coin, where you are in a superposition of states 0 and 1 at the same time, like a spinning coin is somewhat in a superposition of heads and tails states at the same time. Then if you bring two qubits together and entangle them, now you have 4 states, right? Heads, heads, tails, 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 heads, and heads, tails. And this is for 2 qubits. The power of quantum computing is that you can run an operation on all those states at the same time. That's for 2 qubits. For n qubits, you could run an operation on 2 to the n states at the same time. So that is the promise of quantum computing. It sounds very, very powerful. In practice, it is very difficult to unleash this great promise of quantum computing. And that's for a number of reasons. And so it's very much a research area, right? One of the reasons is that qubits are very fragile. They interact a lot with the environment. They decohere quickly. And also, it's not always easy to run algorithms through a quantum machine. Right? If you want to have an algorithm that needs to put a lot of input into the machine, that is actually a linear process, and you're taking away from the advantages you get during the fast computation. It's also a probability-based technology, right? So everything is in probabilities. You need to run your algorithm through many, 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 many times. And still, you will need some sort of filtering or post-selection technique in order to get down to one result. So this is a very rich research area. There are many, many things that need to be solved to enable commercialization of quantum computing in Intel's perspective. So Intel takes a systems approach to quantum computing. I'm going to just walk down the stack and talk to you a little bit today about some of the research and the collaborations that are going on in these areas in quantum computing. Let's start at the top. Intel's very, very interested in what are the compelling application areas. Why would a user want to use a quantum machine? Who are our first customers? As I mentioned, qubits are very noisy, so we're interested in noise-resilient algorithms. Some of these hybrid classical quantum algorithms, where the quantum part is done on a quantum processor, but the classical things that are better done classically are still done on CPU. And I'm particularly interested in what can we do with these small systems of qubits that we have today? What can we run on these small systems of qubits? Can we run representative workloads that are representative of larger, interesting algorithms from interesting application areas, from useful application areas? And by doing that at this stage, can we learn to co-design? Can we learn something about how to design the rest of the computer? Can we learn about what kinds of functionalities will be necessary from the rest of the system architecture? Can we understand what kinds of instructions are necessary to run algorithms from certain application areas? Can we help to co-design the qubit chip itself, and in return, learn from the qubit researchers how to write better algorithms for quantum machines? So we're expecting that, since it is very difficult to unleash the exponential power of quantum computing, we expect that it'll take on the order of thousands of qubits to be able to outdo a classical computer for even small chemistry problems. And we're thinking millions of qubits per commercial scale. Given the promise of massive parallelism, it's not surprising that we think that quantum computing will be useful at HPC centers as a quantum coprocessor, which would augment but not replace your traditional HPC system. So this is actually the open circles on the right our raw data, real data from 5 qubits. This is an application area we're calling materials design, but what it is simulating materials that have unusual electronic and magnetic properties, materials in which electron-electron interactions are very important. And at this stage, we can do just small parts to algorithms that might be useful for these kinds of longer-term simulations. I mean, in future, one of the promises of a quantum computer might be that you might be able to simulate some of these intractable classical problems, like simulating high-temperature superconductors, materials that are have interesting magnetic and electronic properties that are of interest to electronics companies, like Intel. So, oops, do not mean to switch that. The open circles here are raw data from 5 qubits. The algorithm itself was to quantify the entanglement of the system. In this case, that measurement is called Redi entropy. This is actually interesting because that is actually analogous to quantifying the amount of electron-electron interactions in the system. And so that does translate over to a materials problem. When you are simulating natural systems, one of the things that's nice is that in your results, you actually have some results that are not physically possible. So there was a natural way to post-process this data. And so that's why I like to actually show this particular graph, because the yellow dots are after a post-selection process. And you can see that that actually matches very well with the blue line, which is the theoretical, what's expected in theory from this problem. And for those of you who might not be used to seeing a quantum algorithm, we write them as quantum circuits, which you can see on the left here. And here, each line is actually a qubit, so this is a 5-qubit algorithm. And as you go from left to right, you're actually seeing what operations happen to the qubit through time. Another area that we're interested in is noise-resilient algorithms. Here's an example of work on a hybrid quantum classical algorithm. This was done in simulation with noise injected. And this was a quantum chemistry algorithm to approximate the lowest energy state of a chemical molecule. And the interesting thing here was that we did 2 different mappings of this algorithm. It turns out that the mapping that required more quantum operations actually was more resilient to noise, which was counterintuitive. You would think that the more operations that you do to your qubits, the more you're exposed to noise, you would think that would be the noisier algorithm. It was actually the opposite. And we've dabbled a little bit in machine learning. This is a 3-qubit, sorry.
Are you going to tell us why?
This is actually, let's talk about that offline, because
okay.
I don't think that I can explain that very simply.
Okay.
Okay. We're also looking a little bit at machine learning. This is a 3-qubit algorithm, which is basically a quantum neuron. We think that could be a building block for future neural nets. And for our algorithm development, we use our own qubit simulator. It's called the Intel Quantum Simulator. It's actually open source at 01.org. And there are lots of simulators out there, but if you want to play with this, it's available there. You can simulate up to 42 qubits on multiple nodes, up to 29 qubits on a single node. That's typical single and 2-qubit ideal gates, and you can inject noise. So it's out there in case you'd like to play with it. Moving down the stack, looking at optimization at many levels. Actually, one of the things that is interesting about working in materials is that at the algorithm level, it's easier to optimize because your materials are actually in a lattice that has a lot of symmetry, and so there's a lot of redundancy, a lot of times your quantum circuit can be reduced easily. But there has to be optimization at many levels within the compilation scheme. Also, mapping and scheduling mapping and scheduling during this noisy intermediate scale device era is actually very difficult, mapping and scheduling to noisy quantum bits, mapping and scheduling to qubits that have connectivities that are not ideal in most cases. We've done a little bit of analytical studies for scheduling. This was looking at running a QAOA, a variational quantum hybrid algorithm on a one-dimensional line of qubits. And here our constraints were that logical dependency, that of course it depends on the logical order of your operations in the algorithm. Exclusive activation, where we meant each qubit can only be used in one operation at a time. And physical connectivity, in this case we assumed that two qubit gates could only happen between qubits that were adjacent to each other. And then in the graph we were just showing more and more sophisticated scheduling algorithms to try to reduce the number of operations necessary to run this algorithm. We've also done some analytical studies on the impact of the qubit connectivity for the execution time, how that affects the execution time of the algorithm. And here we've looked at 3 representative workloads, quantum Fourier transform for factoring, Jordan-Wigner for chemistry and materials, and Grover's for search. And we've looked at them in the upper panel, the blue dots are qubits, and the lines between them are ones where we say you can do a 2-qubit gate between those, right? So we looked at a line of qubits, a ladder of qubits, a 2-dimensional grid of qubits, and then all connected devices. And the thing that we found that was sort of interesting was that for certain representative workloads, like the quantum Fourier transform, the connectivity, the line actually behaved almost as well as the all-to-all connected device. So those are samples of things that we're working on at Intel. Of course, qubit control is also hugely important, and today, if you go to a qubit lab, you will see, even though we have only small numbers of qubits, you'll see racks and racks of electronics. So this I/O problem, there are many problems for qubit control, but I/O problem is a big one. So we, as a number of other groups, quantum groups, are looking at bringing the control chip inside the chamber to cryogenic temperatures. And the reason there is because, you know, if we're talking, you need about 1 million qubits for a commercial device, even if you have only one I/O wire going into our chamber, our qubits run at cryogenic temperatures, so into a dilution refrigerator. Even if you had only one I/O wire going from room temperature electronics to qubits, you would still have a million I/O wires. And this is really not scalable. So in trying to bring the control chip closer to the qubits, we're hoping to eliminate the need for some of those I/O wires. But this is still an area of research. And likewise, there's the number of interconnects that you need to go from the qubit chip to the packaging. And this is something that Intel's very aware of because of the packaging for its other processor and memory chips. Quantum chips do very poorly here too. They need a lot of interconnects. So something we're looking at. And then finally down to the qubit chip itself. Intel has a lot of expertise in the fab and, as I mentioned, packaging and assembly. We have a collaboration with QTech, with Leo DiCarlo on transmon superconducting qubits, and with Lieven van der Sijpen on silicon quantum dot qubits. This is, in case people have not seen a qubit lab before, here's a person in the lab, and then these big silo-looking things are your cryogenic refrigerators, and you can see some of the electronics racks here and behind, and then some pumps and things. And so it's a huge room, right? A huge lab. So we're working with those 2 types of qubits for collaborating with QTech. I should also mention that it's a collaboration within Intel. So I work at the Intel lab side of the house. the Qubit research, as all materials research, actually happens at the fab at Intel. So looking at two different types of qubits, one on the left, the superconducting qubits, which is a relatively mature type of qubit. It's been around more than a decade. On the other side, silicon quantum dot qubits, relatively immature type of qubit. However, very, very well suited for Intel fabrication. It is like fabricating a one-electron transistor. So we feel that we have a lot of expertise in that area. Our progress, Intel's been in the quantum computing arena for less than 5 years, and this was kind of our progress on the superconducting side of things, going from a component of qubits, resonators on this chip, all the way to 49 qubits for Tangle Lake. On the silicon quantum dot side, we've set up a 300 millimeter process node, a fab for silicon quantum dots. We're using isotopically pure silicon-28. We're seeing these really clean line shapes, which you'd expect from Intel fab. Also, we are doing mask designs and all of that. This is actually, I think, an 8-inch chip, test chip, with each. This rectangle is 200 quantum dots across. And so we have the whole testing infrastructure and fabrication infrastructure is natural for Intel. I also wanted to mention that quantum computing, of course, was originally a physics discipline. I'm really happy to see it in quantum computing starting to appear in a computer engineering venue. I think that's super important. Physicists, I'm a physicist. Physicists tend to be either interested in the qubits themselves or in the algorithms. So if you ask us for to set metrics, a lot of times we're very much interested in how long does my qubit live? What's the decoherence time? How many qubits do I have? What's the physical qubit count? I'm really happy to see things starting to move towards system. We're starting to talk about gate fidelity and gate operation time and number of logical qubits and things like quantum volume. I think these are all really good steps. I would really like to see us talking about system level performance, right? I'd like to see us thinking about how well does the algorithm perform through the whole system, right? And this is something that we're starting to look at. Can you do a system performance simulator for small numbers of qubits? So in conclusion, I think the potential of quantum computing is generating a lot of excitement, a lot of hype. I think that for those computer engineers out there who are interested in learning a little physics, or vice versa, physicists who are interested in learning computer engineering, this is really a rich research area. It's a lot of fun, and I highly encourage you to try to get into this field. It's so wide open in a lot of ways. Intel is doing a good job of leveraging what we're good at fabrication, at packaging, at architecture. But a commercial system is still quite a ways into the future. Thank you very much.